A digital image is represented in a 2D grid of pixels, where each pixel includes the brightness and the color. Each and every pixel can store 8-bit information if it's a grayscale image, where 0 will indicate black and 255 would indicate white, and all the colors in between will indicate different shades of gray. To represent three channels RGB for a color image, I will use 24-bit for each and every pixel. Now consider if I include 24 bits for each and every pixel, and no, there are going to be thousands of pixels, 1000 by 1000 pixel image. It is going to occupy a lot of space. And consider a video, which is a video is nothing but several frames in motion, giving the video effect. And so in videos, frame is nothing but a single still image, and it is indicated by frames per second. That is, how many frames are shown per second is indicated by fps. So consider if I make use of 1920 into 1080 frame size, and 24-bit representation, which is going to be 6.2 MB. 1 second of raw video, 30 frames per second, will take 186 GB, and 1 minute is approximately going to take 11 GB of size, which does not usually happen, and which is too large a storage to be stored. And so we go for compression techniques. So under compression, we try to find and remove redundancy. Redundancy in English terms generally means any kind of repetition, and here we try to eliminate that kind of redundancy without discarding information that is there. Let's say if I have a 2 GB video and I reduce it to one size, so the original size is 2 GB and the reduced size is 1 GB, and so I get the compression ratio of 2:1. So data redundancy works with four ideas. One is coding redundancy, that is equal length codes for unequal probability symbols. Consider in an image red is more, but still R, G and B, all the three will carry equal length codes, or consider red is very prominent. So what if I can give a shorter code to a more frequent symbol? The another idea that which gets used in data redundancy is interpixel or spatial redundancy. That is, whatever are the neighboring pixels, they are very much similar to each other. We can also make use of psychovisual redundancy, that is, the human eye cannot perceive everything equally, like small differences in color are not perceived to the human eye. And the last one is temporal redundancy. Temporal means related to time. So consecutive video frames are very much identical. So coding redundancy indicates that if every symbol uses the same number of bits, we based bits on rare symbols. Consider letter E appears far more often than Z. So there is no point giving 8-bit symbol to each. What if I can give, let's say, a 2-bit symbol to E and an 8-bit symbol to Z? Another way to reduce spatial redundancy is where we consider that the neighboring pixels are very similar to each other. Is Consider if I have rows something like 200, 201, 200, 199, 201, and so on. I can make use of run length encoding or predictive coding or LZW coding, where the similar values are getting repeated, and so I can make use of that idea and make it uniform. The next one is psychovisual redundancy. Now psychovisual redundancy means the human eye, it is less sensitive to color detail, but it is very sensitive to brightness. We should keep this idea in mind when we are working with videos also, that the human eye is not very sensitive to color details, but it is very sensitive to brightness. We can remove a lot of color detail from a photo. So this is the idea that's being made use in quantization, chroma sampling. Here we make use of this particular idea. And temporal redundancy is based on for videos only. Like consider two consecutive frames of a news anchor talking. Now, here the background is not changing. So, here temporal redundancy means I make use of the idea of motion estimation, motion compensation. Like, consider if a car is moving, it was at location X, and after 2 seconds, it is at location X plus 20. After 2 seconds, the car is now at the location X plus 20. I make use of this particular idea, and instead of coding and reconstructing and instead of storing each and every frame, what if I can reconstruct the frames from 0 to 2, because anyways the car is going to move slightly. So the general compression pipeline is, first of all, we perform mapper, that is we re-express the data so that we can perform coding on it, and then quantizer, that is this is one of the lossy steps, that is it leads to loss of information. Compression can be of two types: lossless or lossy. Lossless means here there is no loss of information at all, like in the case of 2 is to 1, 4 is to 1, very simple techniques. Bit for bit deconstruction is possible. But in the case of lossy, where I go for higher range of compression, some kind of higher range of compression, some kind of loss of information might be seen. So in quantizer, where I'm trying to reduce precision, it is a lossy step, that is I might try to reduce the precision. And then there is symbol or entropy encoder. So, and here it will give short codes to frequent symbols, removing coding redundancy. So, lossless compression does not lead to loss of information, and not much of compression ratio is possible. Example: Huffman, RLE, LZW, PNG compression, zip compression, all these. This we will see this. Uh, what are these particular techniques in the following videos. Then we have lossy type of compression. Approximate reconstruction is possible, like 10 is to 1, 100 is to 1, JPEG, MPEG, MP3, all these make use of lossy compression. So these are used for photos, streaming videos or audios. Compression measuring, how has the compression been, can be done with the help of compression ratio. Original size is to compressed size. Average bits per pixel, like earlier it would be 8, now it would be reduced to 2.3 or something. Entropy is given by minus summation of pi log pi. So it leads to minimum bits per symbol. And then there is coding efficiency, h by l, where l is the actual average code length that's achieved. We will see how do we calculate this. One another measure that gets used is PSNR, peak signal noise ratio. Now this PSNR, it's an objective mathematical calculation. The formula is given by 20 log 255 divided by root MSE to the base 10. So 255 in the formula is the maximum possible pixel value for 8-bit images. Now what happens over here is, consider if it's a total reconstruction. Now original minus compressed will be 0. MSC will become 0. And so this whole log something divided by 0, and so it becomes log infinity. It becomes infinity. This whole equation reduces to infinity. So in case if it is lossless compression, where original and compressed are both same, MSE becomes 0, and so PSNR reaches infinity. So MSE is equal to 0 when original is equal to compressed pixel for pixel. Usually if I have a PSNR value of 40 plus, that means it is a good compression.